In this video, we are going to use double integrals to find volume, area, and average value. This is going to require the same discussions of type 1 and type 2 regions that we've been having, and all of our integration techniques as well. Starting off, find the volume above the xy plane bounded by the parabolic cylinder y equals x squared minus x, and the planes y equals x and z equals x plus 4. So in this example, we have three surfaces as well as the xy plane that defines the solid whose volume we're trying to find. Our first task is going to be defining the region of integration. That will also be the area of the base for the volume. Looking at the surfaces, we're going to focus in on y equals x squared minus x and y equals x, since those will have curves in the xy plane, and we'll see if those two surfaces will produce a region of integration. So, helpful to draw a picture here. So we have our x, y, just the first quadrant, graphing that parabolic curve, 0, 0, and 1, 0 would be the intercepts. So then we can draw our parabolic curve through those points. So there we have y equals x squared minus x. We'll also graph y equals x. So we have a nice closed region, and this is going to be the region of integration. There are 2 points of intersection here and here. We do need to find those, so now is a good time to do that. Substitution leads us to x squared minus x equals x squared minus 2x equals 0. Factor out an x times x minus 2, so x equals 0 or x equals 2. So 0 and 2 are the x values of those points of intersection. If we need the y values, we could easily find them by plugging in, especially to y equals x. This region is going to be more easily defined as a type 1 region. So we can draw vertical lines throughout the region just to indicate that. And that will help us set up our double integral for volume. So we have the double integral from x squared minus x to x from 0 to 2. Now, our next task is figuring out what we are integrating to find the volume. So the surface we haven't used yet is z equals x plus 4. It is a z equal surface, so the z value would be above this region, and that surface is going to define the height of the solid. So that's what we want to be integrating over this region, right? Area of the base times the height is a simple way to define volume. So then we're integrating x plus 4. As a type 1, we're going dy dx as our order of integration. So integrate with respect to y gives us xy plus 4y from x squared minus x to x dx. So now substituting those bounds in, we get x squared plus 4x minus x to the third minus x squared, so plus x squared, and then minus 4x squared, and then plus 4x dx. Let's combine our like terms before we integrate. Less integration to do. So negative x cubed, and then we have negative 2x squared plus 8x dx. And now we're going to integrate that with respect to x. So that's going to give us negative 1/4 x to the fourth minus 2/3 x to the third plus 4x squared evaluated from 0 to 2. So that's going to be 16 times negative 1/4 is negative 4. 2 cubed is 8, so 16 over 3 minus 16 over 3. 4 times 4 plus 16, and substituting 0 into all three terms would give us 0. So it's going to be 12 minus 16 over 3, which this is really 36 over 3. 20 over 3 is the volume of the solid with the region that we defined as the base, and then x plus 4 as the height. All right, so the volume bound between x plus 4 and the xy plane over this region. Our next example, find the volume bounded by the surface z equals 5x plus y squared, the parabolic cylinder x equals y squared, and the planes z equals 3x and x equals 1. So here we have 4 surfaces that define the volume. Again, we want to focus on surfaces that may be helpful in defining the region of integration. So for me, x equals y squared and x equals 1 stand out there. So if we sketch those 2 curves in the xy plane, so x equals y squared would give us a parabolic curve there. So x equals y squared, and x equals 1 would be there. So we do have 2 points of intersection. I think we could figure out what those are, but just to be complete here, we'd have y squared equals 1. So y equals plus or minus 1. So negative 1, positive 1. And again, if we need the x values, we already know it's x equals 1 there. I do think this region makes more sense as a type 2 region, so going from left to right throughout the region. Now, just something to note, it doesn't show up in this example nor the previous, but you might look at your surfaces, draw the curves in the xy plane, and you might not get a closed region. In that instance, you're going to have to look elsewhere for another curve that's going to close off your region of integration. Often, that's going to be finding the intersection of surfaces that you didn't use yet. So for instance, let's suppose this wasn't a closed region, we might have to find the intersection of z equals 3x and z equals 5x plus y squared. That intersection will draw on the xy plane and hope that it closes off the region of integration. So just something to watch for. Not every problem is going to work out as nicely as these two have. So now we're going to set up our double integral. Actually, before we set up our double integral, I do want to point something out. There are 2 surfaces now that we haven't used. We were just speaking on those. So this example is volume between 2 surfaces. So just like in single variable calculus, you found the area between 2 curves, we can find the volume between 2 surfaces. So in this case, the surfaces are z equals 5x plus y squared and z equals 3x. So this does add another decision-making step, and that is deciding which of these surfaces is on top and which of these surfaces is on bottom over this region, because it could change elsewhere, but we're only focused on this particular region, the relationship. So in this case, 5x plus y squared is going to be larger than 3x over this whole region. At times they'll be equal, right? At 0, 0, for instance, z would be 0 for both surfaces. Okay, but that means that this is going to be the top surface and this is going to be the bottom surface. Now with that decided, we can set up our double integral. So we have the double integral going from left to right. We're going from y squared to 1 and then negative 1 to 1 along the y-axis. And then just like area between curves, where it was top minus bottom, volume between surfaces will be top minus bottom. So we have 5x plus y squared minus 3x dx dy. And if it were necessary, make sure you have parentheses so that you would distribute the subtraction sign appropriately so that you have all of the correct signs for each term. So we can clean this up before we start integrating. So that's going to be integral from negative 1 to 1, y squared to 1 of 2x plus y squared dx dy. And now we begin the process of integration. So integral from negative 1 to 1 of x squared plus xy squared, going from y squared to 1 dy. And that's going to be the integral from negative 1 to 1 of 1 plus y squared minus y to the 4th minus y to the 4th dy. Again, combine our like terms before we proceed. So 1 plus y squared minus 2y to the fourth dy. And we integrate with respect to y now, so y plus 1/3 y cubed minus 2/5 y to the fifth, evaluated from -1 to 1. I'll move over to this side a little bit further. Okay, so because all of these are odd terms, we're going to get the same values plugging in 1 and then minusing, plugging in -1. So what we can do to simplify the plugging in part is we can just double what we get by plugging in 1. And if what I just said doesn't really make sense, I would encourage you to plug in 1 and -1 and see that the result matches what I'm going to show. So plugging in 1, we get 1 plus 1/3 minus 2/5. And then if you plugged in -1 with the subtraction, you would also get 1 plus 1/3 minus 2/5, because all of these are odd terms. So then we can just double what we get by plugging in 1. So that's going to be 2 times, let's see, common denominator 15. So 15 plus 5 would be 20, minus 6 would be 14. So 14 over 15. So 28 over 15 is the volume bound by those two surfaces over the region we defined in the xy plane. Okay, so we had volume bound by one surface and the xy plane. This example is volume bound by two surfaces, and we also spoke about the instance of drawing a region that's not closed and how you would proceed from there. Now let's move to area. So if R is a closed and bounded region and the function is equal to 1, then the double integral of the function f of xy dA over the region R, we can replace with 1. So double integral of 1 dA over the region R, and this represents the area of R. Really, it's still a volume, just to be clear. Double integrals represent volume. But if we think of volume as area of the base times the height, if the height is 1, then the area of the base is equal to the volume. And we're using that fact to then say, well, then this double integral is a double integral that represents the area of the region that we are integrating over. So this just gives us another tool to find the area of a region. You could do it with single variable calculus still, right? You have all of those tools available to you. Find single integral, define your top curve minus your bottom curve. This is just giving us another option, a double integral to find the area bound by curves. So find the area bound by the curves y equals x to the fourth and y equals x. So y equals x to the fourth, x, y. So a little bit more flat there. So we have y equals x to the fourth, and then y equals x. Gives us a little narrow region there, but we have 2 points of intersection. Again, a little algebra to find them. So x to the fourth equals x. X to the fourth minus x equals 0. Do not divide by x. You'll miss one of the answers. So x times x cubed minus 1 equals 0. So x equals 0 or x equals 1. So 0, 1. Type 1 region, I think, is simpler, although this could be done either way. So we're going to set up a double integral for area now. So double integral going from x to the fourth to x, 0 to 1, of 1 dy dx. Right? So all that's going to change in an area double integral are the bounds. You're always going to be integrating 1 and maybe the order, right? You might go dx dy if the region makes more sense or is simpler as a type 2 region. So integrate with respect to y. So we get integral from 0 to 1 of y, evaluated from x to the fourth to x dx. So the integral from 0 to 1 of x minus x to the fourth dx. Integrating with respect to x, we get 1/2 x squared minus 1/5 x to the 5th from 0 to 1. So that's going to be 1/2 minus 1/5, and then zeros. So common denominator of 10, this one I'll write out. So 5 over 10 minus 2 over 10, 3 over 10. So the area of this region bound by these two curves is 3 over 10. Now finding the area is going to be helpful as we move into our next piece, which is average value. The average value of a continuous function f of xy over a closed bounded region R with positive area is 1 divided by the area of the region times the double integral of the function over the region. This area might be geometric, so you might be integrating over a rectangle. Find the area of a rectangle. That's not going to require a double integral. Maybe you're integrating over a triangular region. Find the area of the triangle, right? So if you can find the area of the region with a geometric formula, do that. You do not always need to use double integrals. If your region is not one that we have a formula for, then just like on the last slide, to find this area, you would have to use the double integral of 1 dA over the region R, okay? Which is what's going to happen in this example because we're just going to build off of the area that we found on the previous slide. But as you look at examples and practice with this, if your area can be found by using base times height or 1/2 base times height, then do that. That's going to make your life easier, and you're only going to have to complete one double integral. So find the average value of the function x plus y over the region R bounded by the curves y equals x to the 4th and y equals x. So we already have that the area is 3 over 10 from the previous slide. We already have the region defined as well, so we don't need to draw it out. We can go right to our double integral. So we said that that was from x to the 4th to x from 0 to 1. And now we're integrating the function whose average value we're trying to find, which is x plus y, and dy dx. So just go through the process of integration. So 0 to 1, xy plus 1/2 y squared, evaluated from x to the 4th to x dx. So that's going to be the integral from 0 to 1 of x squared plus 1/2 x squared minus x to the 5th minus 1/2 x to the 8th dx. Okay, we can combine like terms before we integrate. So that's going to be 3 over 2x squared minus x to the 5th minus 1/2 x to the 8th dx. And integrate with respect to x. So that's going to be 1/2 x cubed minus 1/6 x to the 6th minus 1/18 x to the 9th. Evaluate that from 0 to 1. So 1/2 minus 1/6 minus 1/18, and then 0 terms. So that's going to be 9 over 18 minus 3 over 18 minus 1 over 18, 5 over 18. Okay, so we have the value of this double integral, we have the area, so then the average value, I'll use this space right here. So the average value, let's use a different color, use blue, so the average value is 1 over the area, so 3 over 10, times the value of that double integral, which is 5 over 18. So 10 over 3 times 5 over 18. We can reduce a little bit, so that's 9 and 5. So the average value is 25 over 27. Right? So this particular function has an average value of 25 over 27 over the region defined by x to the 4th and x. All right? So everything kind of ties together. You'll notice all of the integrals are very similar here. We didn't have a lot of natural log or e to the x type integrals, although we could. We kept it very consistent in this video. Volume, then volume between two surfaces. That led to area by defining the function equal to 1. And then we use that to help us find the average value of a function over a given region. So with all this, practice more so that it makes sense. You see different setups and different situations, and then practice your integration techniques as well. See you in the next video.